Okay, today we are going to derive the continuity equation in three dimension, or we can say cuboidal element. Okay, suppose we consider a small element whose length is dx, width dy, and height dz. Okay, the fluid is flowing in the x direction with the velocity u, in y direction with velocity v, and in z direction with velocity w. Okay, since continuity equation is based upon the law of conservation of mass, which says that mass can neither be created or nor be destroyed. Okay, it only transform from one form to the another form of energy. Okay, so in starting, the mass flow rate which is flowing, or we can say which is enter in the cuboid from face a b c d, is denoted by m dot x in x direction, that is rho area into velocity, density into area into velocity. This is the mass flow rate in x direction. As we know that the velocity in x direction is denoted by u. Okay, and the area of a b c d is dy into dz. Okay, and rho is the density. This is the first equation. Okay, similarly the mass flow rate which is leaving the box from face E, F, G, H is denoted by m dot dash x in x direction, that is rho into area into velocity dash. Okay, area is similar to for starting. Okay, the density into area, that is dy into dz, or velocity. There is some increment in the velocity, that is which is the velocity. Okay, there are some difference in the velocity of the starting portion and the end portion of the cuboid. Okay, the end portion velocity is u plus del u upon del x dx. Okay, so also we can written as dy dz plus rho dx dy dz. This is the second equation. Okay, so the increase in the mass flow rate in x axis, or we can say in x direction, is increase, that is the x increase, that is plus. Okay, so we can say the first equation minus second equation. Okay, d was minus okay, then the net increase in x direction is del upon del x rho u dx dy dz. That is the, this is the third equation. This is the increase of the mass which is flowing in x direction. Okay, similarly in y direction, then increase in the mass in y direction is del, in y direction the velocity is v. Okay, similarly this is dx dy dz with respect to in y direction the width is dy. Fourth equation, similarly in z direction, omega is the velocity in the z direction and width is dz. Okay, okay, then the net gain in the mass of the cuboidal element equals to 3 plus 4 plus 5, that is net gain equals to minus upon this is common in all three equation dx dy dz, so we can out of the box, so we can okay dx dy dz, okay, sixth equation. So as we know that the mass is conserved in equation, so as we know that the mass remains conserved, so mass can neither be created nor be destroyed. So from where this mass come, okay, so we can say the net gain in the increase of the mass in x direction, y direction and z direction is equal to the total increase in the mass of the cuboidal element, okay, per second, okay. So the total mass increment in cuboidal element is denoted by per second, that is per second, that is rho density into volume per unit time, okay, dx dy dz, okay, per unit time, that is t then t, okay, we can say. So this net gain is equal to the total mass of the gain of the cuboidal element, okay. This is the seventh equation, so we can say sixth equation is equal to the seventh equation. On there we can write as dx dy and dz equals to dt dx dy dz. This is same in both sides, okay, so we cancel out this from, okay. Now for a as we say, for we consider some steady flow, we consider the fluid flow through the cuboidal element is steady in nature, which means that the characteristic properties of the fluid remains constant, that is the pressure, velocity, or we can say density is remains constant with respect to time, such that we can say that this portion is equal to 0, okay. Now the equation becomes this portion, we can put this equation in this side, plus 10 plus del rho upon del z equals to 0, okay. For an incompressible fluid, okay, now we can consider the fluid which is flowing through the cuboidal element is incompressible in nature, which means that the density of the fluid remains constant, that is rho remains constant, okay. If rho is constant, so we can put outside of this differential equation, okay, and it is equals to 0, and it as we know that, sorry, it is not equals to 0, as we know that rho into del u upon del x plus del v upon del y plus del omega upon del z equals to 0, as we know that the density of fluid not equals to will not equals to 0, so this portion is equals to 0, okay. So this is the equation of, that is this portion, this is the continuity equation for three dimension in case of steady flow or a incompressible fluid, okay.